This one thinks it's 75%, so it should charge my plug your stack in.
I know.
I lost my pencil lab.
Whoa. Uh-oh.
Hey.
You're going to need to use this, huh?
Oh,
Wait.
maybe.
Wait. We can do it another way. We can do it maybe like that.
Nice. Doesn't look like
Then
it'll work.
maybe like that. Hey.
Brilliance.
That works. And then...
Are you going to use the down screen today? Oh yes, obviously
What
you
am I
will
gonna
be.
do?
Nothing. You're gonna use the projector, which means
Yeah.
you're only gonna write
That's
over
my
here.
hope. Okay, you get set up. It'll take me longer.
I think I'm set up.
You're set up?
I believe so.
No kidding.
Yep, because you only write over here, so it'll be really easy
Yeah.
for me.
I'm stuck because as soon as the screen comes down, that's the end of it.
Perfect. Hopefully you can hear us. I think it can. Speak up.
Okay, so let me turn this on again. It asks me, Sam, do you know how to prevent this thing from asking me for my password every time it comes back from sleep? Yeah, okay, we'll consider that.
It's in your preferences menu. I can show you later if you want. I'm pretty sure it is. Does it hibernate and go back to its default settings every time? Is it one of the is it like a school computer or something?
IT people screwed with this thing, and it's never been the same.
They probably put a deep freeze on it so it
They
resets your
did
setting
something
all the time.
Terribly nasty.
Deep freeze is
Very
terribly
nasty.
nasty.
So let's turn this on. Let's go to PC, and now let's see if it stays where I set it. I doubt it. But we'll see. Here goes nothing. Didn't go, yeah. You garbage. All right. Let's see if it goes. Yay. Okay. Oh, right. What's this? We don't want this. Okay. There we go. Are we set? Okay. We are going to spend this week going over the meat of this topic in my estimation. We've already covered preparation reactions of aldehydes and ketones. We've covered characteristic reactions that ordinary aldehydes and ketones undergo. And now we're going to talk about what you see here on the slide is carbanion-related reactions. And you need to appreciate not necessarily aldehydes and ketones, but any carbonyl-containing species. So, when I say carbanion-related reactions, what am I saying? Here is my carbonyl group, and if next door I have a set of alpha hydrogens on the carbon, alpha to the carbonyl, okay, you need to appreciate that these hydrogens, especially in the presence of base, can be removed so that I generate a carbanion. That carbanion is adjacent to a carbonyl pi system. And whereas negative charge on carbon is not ordinarily something that carbon is pleased to tolerate, when you have that adjacent pi system, you can have, without mentioning the phenomenon, you can have something that looks like this. The combination of the two structures is an attempt to indicate that that negative charge that we created under basic conditions is being delocalized. And under those conditions, the carbon next to the carbonyl will tolerate that negative charge. Right? So that's the first point I wanted to make. That you can generate alpha carbanions. But now the question is, so what can you do with them? Well, the answer is, we're in the business of building bigger and more complicated structures from simpler structures. Up until now, what was your principal carbon skeleton building reaction? Grignard. Exactly. Well, we're going to expand on that now. So let's show. Why is the screen blank on this?
As long as the green light's on.
All right. So let's show you. If I have a molecule of some species, for the sake of simplicity, let's consider it's an aldehyde. Okay? Here's an aldehyde. And here used to be a CH3 that I've succeeded in removing a hydrogen from. Incredibly bad English, but we'll go there. Right? What if I didn't turn every last one of my original aldehyde molecules into a carbanion? Let's say there's only a small population of carbanion around at any one moment. Now, here is the rest of the population. And if the object is to create a bigger and better carbon skeleton, here are the ingredients that do just that. What, you ask? Well, this C double bond O is a polarized bond. Which end is electron deprived?
Carbon.
What's that? Electron rich or electron poor?
Electron rich.
What? I heard that. Okay. Electron rich. So, here is your reaction that builds the carbon skeleton. So, you now have CH3. You now have CH. Here you have, temporarily, O minus. Here is the most important thing. Let me just, is this actually right? Yeah, maybe. Oh man, it's the wrong color. Okay. So here's the bond we built. Here was what did the attack. Here's the baggage it brought along. And when you work this up with aqueous medium, this becomes, instead of O minus, it becomes O8. So eventually, we're going to end up with a species like this. So the point is, from two molecules of this originally, a little bit of basic medium, and I can build my carbon skeleton. This is called a carbanion attack on carbonyl. And you'll see that this theme, more or less, will run through the bulk of the reactions that we're about to discuss. Does everybody feel comfortable with this fundamental concept, though? You good? Okay. So, question. Thank you for reminding me. Otherwise, it would just sit there.
He comes around and gives her another 3 copies.
Everybody in possession of one? Oh, good, that's good. All right, so now at least you'll be able to flesh it out as we go along. All right, so what are we going to be talking about? We're going to be talking about, and by the way, once we finish with the topic and before the exam, you need to feel absolutely confident that when I say the phrase aldol condensation, a specific reaction pops into your head. You have to be able to associate the chemistry with the terminology. So, aldol condensations come in two varieties called self versus cross. The next one goes by a proper name. It's called a Claisen condensation. Again, self versus cross, along with a specialized version of it called a Dieckmann cyclization. What do you think we're making in a cyclization?
A cyclic compound.
Yeah, we're making a ring. That's what we're doing. Okay. For what it's worth, to use non-technical terminology, think of the cyclization reactions that we're going to encounter as dog biting tail. That usually gets the job done. Okay. Then we have another proper name called the Reformatsky reaction, which I hope to convince you is really a sort of hybrid of the previous two. Then we have yet another proper name called the Wittig reaction. I should tell you that just as Grignard was awarded a Nobel Prize for his carbon skeleton building work, Wittig, a Romanian chemist, was also awarded a Nobel Prize for his work. And here we have a number of miscellaneous alkylations and acylations and conjugate additions, whatever that is, that we'll talk about. Not this evening, I assure you. It'll probably have to wait until Thursday. Okay, but that's what's ahead of us. Anybody need to ask a question at this point? If the question is why, the answer is too bad. Okay. We need to. All right. So let's get into this. Yes, let's get, oh, that was a nice transition. All right. So what's going on here? Notice in this first example, I'm using only one starting material. Two molecules of it, but only one starting material. One of them under either basic, well, let's put it this way. The reaction can happen leading to this ultimately under either basic or acidic conditions. Under basic conditions, one of these two starting molecules will be turned into the carbanion species that will then attack the carbonyl group of the one that wasn't turned into a carbanion. That's the easier mechanism to appreciate. I will also show you how the reaction actually happens under acidic conditions, why you can't see the positive charge. Right. So this one, as you'll see momentarily, is called the self-condensation. There it is. This one, if you look very carefully, uses two different starting materials. But notice something. Despite the fact that you have two different molecules, how many alpha hydrogen environments do you see amongst all the starting materials? Alpha hydrogen environment. One. Does this molecule have an alpha hydrogen environment? No. Because on the carbon adjacent to this carbon, notice I've purposely made it impossible for you to judge. Take my word for it, there are no alpha hydrogens here, but here you explicitly see those alpha hydrogens. So, why is this combination going to work, you might ask? Well, because only one of these two reactants can generate the carbanion. Agreed? All right. But the question then becomes, because those carbanions are not generated all at once, and because those carbanions aren't going to be coming from each and every molecule of starting material, the question that you might want to ask yourself is, so what's to stop a carbanion that was generated from this from attacking a molecule of this that hadn't yet turned into carbanion? Aren't I going to get a mixture of products that you know your instructor will simply not tolerate? So how do we get around this? I'll address all of that as we go through this. All right? Still with me? Let's do it. Here we go. So this one is nearly identical to the example I used a moment ago. So here we have RCH2, here's H, and here would be the counterpart of this after base succeeded in removing one of the two alpha hydrogens. Here is my stabilized carbanion, and it's now ready to attack. So the attack occurs, the pair of electrons is localized on oxygen, so we now have the following. Here is my newly created carbon-carbon bond. Here is CH with baggage attack. Here is C double bond O. Here is H. And as soon as I work this up, that's going to be the product of my aldol condensation. How does one describe this kind of product? Well, if this is the alpha carbon, what's that?
Beta.
Beta. So, what kind of family of compound is it because of this?
An aldehyde?
Aldehyde. So this is some kind of aldehyde. What kind of aldehyde? What's this? A beta hydroxy. Beta hydroxyaldehyde. So the typical product of an aldol condensation is either a beta hydroxyaldehyde, or under the right circumstances, it could be a beta hydroxy ketone. Can you think of an example where the sole product of the aldol would be a beta hydroxy ketone? In other words, if the whole criterion for avoiding mixtures of products is to ensure that there be only one alpha hydrogen environment in all of my starting materials, think of a ketone that would satisfy those demands. I'll give you a hint. Say again? What do you mean a tertiary?
I mean,
There's no such thing.
If you had trisubstituted carbon, so if it was a ketone that had 3 other carbons attached to it, it would be
You mean a terpetal group? Yeah.
Yeah, that's what it's good.
So you want to go with something that has alpha hydrogens and a terpetal. So hang on. Let's see what we're coming up with.
Does it have to have only carbons attached to it? Oh, well.
Wait. Let's just do this. So we're talking about CH3 taken 3 times carbon. That's terpetal. Here's my carbonyl. And here is my CH3. That's my source of alpha hydrogen, right? And if I used a second molecule of this that now has been transformed into carbanion, that carbanion would look like this. CH3 taken 3 times. And assuming this happens, although I'd have my doubts because this is already a rather sterically hindered carbonyl system, but for the sake of our discussion, we're not going to worry about that right now. That's gonna happen, that's gonna happen, and that's the only thing that can happen, right? So what are we going to generate? We're going to generate something that looks like this. Here eventually will be an OH. Here is the CH3 that came along for the ride. Here is the bond that this carbanion carbon created. So here's my CH2. Here is my carbonyl. And here is the baggage. I'm running out of room, so be lazy. Just put down tricky. You draw that nicely. So I get one and only one condensation product. Are we good with this? Okay. That isn't exactly the ketone I had in mind. You can try this for yourself. The simplest of all the ketones would be acetone. Okay, so you're going to do this exercise for yourself. How many alpha hydrogen environments that are unique are present in acetone? Answer, 1. Doesn't matter which of the 6 hydrogens you rip off, you're going to generate 1 carbanion and only 1. That's all that this cares about. We good? Okay, so now, let's come back to the following. Let's say that instead of acetone attacking itself, what if I said, let's have acetone attacking the following? Okay, this is an aldehyde. This is a monosubstituted benzene ring. Are there any alpha hydrogens in this structure that could be ripped off to generate a carbanion from the aldehyde?
No.
The answer is absolutely not. Okay. But you've already been told that in the presence of base, that acetone can attack itself. So if I write this, then am I not going to get more than one condensation product? And especially if the question is such on your exam, there's only one space waiting for you. And if you're thinking, well, maybe there's more than one product that ought to be formed, in other words, the carbanion attacking this, the carbanion attacking the second molecule of that, there should be 2 answers. But it's all in the way this is done. Ready? If you're going to limit yourself to just one product of the condensation, what you do is you have a beaker or a receptacle of some sort. Here is where your base happens to be. And your base is going to be mixed in with which one of those 2? And the answer is going to be the one with which the base does not react. Which is that? The acetone?
No.
Just the wrong answer. Absolutely reversed. This. So in other words, you put the benzaldehyde in with the base. Where are the alpha hydrogens that the base is looking for? The answer is there aren't any, so it just sits there. Okay? Now what do you do? Now what you do is you come along and you literally drip in the acetone. Drop by tedious drop. When the drop of acetone hits this medium, there's enough base to do what to that drop of acetone?
Strip it
I'll
of its
start you
hydrogen.
off. Turn
Carb-
every last molecule of acetone into what? Carbanion. Can't attack itself. See? Logistics plays a role here. Right? So that's how we're avoiding getting mixtures of products. It's the order of addition. The one with the alpha hydrogens gets added to the basic mixture with the one that doesn't have the alpha hydrogen. So that being the case, can you predict for me what my condensation product will look like? And this is a question of training yourself to visualize how this is all happening. So, which one of these two is forming the alpha carbanion? And where is it being formed in the acetone? So, what can you write mindlessly to get your product structure started? How much of that structure can you do without too much thinking? What can I write first? What? What can I write first?
CH3.
CH3. Yeah, what else?
Carbonyl.
C what?
Double bond O.
C double bond O. And instead of writing CH3 again, you'll write CH2, but you're not going to write minus because you're writing the final product already. You're going to say, okay, yeah, for emphasis, a big bond. And where did that CH2 carbon attach itself to that?
COH.
To this carbon, former carbonyl carbon that is now no longer a carbonyl, but it ended up,
CO minus.
no, we're going for the bitter end.
Carbonyl.
Carbonyl, and the baggage that it brought, still there. So here's this, and here's this. And ordinarily, this would be the right answer. Ordinarily. But there's a catch here. Right? But this is the way I wanted to train you to start thinking about doing these problems. Just mindlessly putting it together. It turns out that what you have here, I'll redraw this like this. Can everybody see it waiting to happen? Yeah. Now, why would this product even think of losing a molecule of water? Well, if you look very carefully, let's do like this. Here's CH3, here's carbonyl, here is CH. What will happen when I lose water? Double bond. So the CH, so the CH is going to be conjugated with how many pi systems? This CH-CH system, conjugated with the pi system, conjugated with the benzene system. Nature loves this stuff. In fact, you would be hard-pressed to isolate any of this if you've been cooking this stuff up, because it's just going to dehydrate on its own. So with benzene systems, this is a major problem, unless this is what you really wanted. Okay? The trouble is, if I say make this, notice how it adds an extra layer of thinking that's going to be involved, because if I tell you that the product of an aldol reaction is typically a beta hydroxy aldehyde or ketone, and you look at this, you say to yourself, where's the beta hydroxy? I don't see any hydroxy. And unfortunately, that's because it's already been lost. But you need to be aware that this is going to happen, and I've got it out in the open earlier rather than later. Okay. So the second one, based on what we just did, is the one that's called the cross condensation. And again, here, without the benzene to interfere, we are in fact getting a beta hydroxy carbonyl product. Questions about the carbanion approach to the aldol? Anybody? So what you need to feel comfortable doing for yourself is, if I show you or tell you what the starting materials are, you should be able to predict what the product looks like. And likewise, if you know what the product ought to be, you should be able to tell me what the starting materials must have been. And this is the skill that you're going to ultimately develop before the end of next week. Okay. Still with me? All right. So now we need to address this other question. It says that this reaction can happen under acidic conditions as well. Well, guess what kind of intermediate will never happen under acidic conditions? No carbanions. Impossible. So, how does this carbon skeleton get put together then? So, let's go with acetone. Okay? Here's an acetone molecule. I'm in acidic medium. What can the acid proton do to an acetone molecule? The only thing it can do.
Protonate its own.
Protonate a basic site. What's the only basic site? The carbonyl oxygen. So you ready? I can turn some, not all, but some of my acetone molecules into the following. That carbocation. Good or bad?
Great.
It's tremendous. Why?
Heterostabilized.
Because it's a heteroatom stabilized carbocation. This will get tiring after a while, but at least it'll have made its impact. Yeah, this is wonderful, right? But if that's all that happened, how's this going to help build the skeleton? Well, the answer is that now what can happen is carbocations, not being happy being carbocations, no matter what is stabilizing them, have the option of getting rid of that positive charge by getting rid of a proton from next door. If I got rid of that proton, big deal. I'm right back where I started, accomplished nothing. But do I have other hydrogens next door? If I lose one of those as a proton, what do I generate? I generate something that looks like this. Here's the OH, but here is this, along with a proton. What kind of species is that? An enol. But think of it as an alkene. Right? This is a region of high electron density. What's that?
Carbocation.
And what's the carbocation looking for? Where's it going to find it? And now comes the real question to see whether all your background has done any good. When this carbon, looking for electrons, attacks this carbon-carbon double bond, which of these two carbons is the one attacked and why? This carbon is going to attack this carbon and put the positive charge over there. Anybody believe that? I send you back to organic 1. This carbon is only going to attack there in order to put the positive charge where?
On the heteroatom stabilized.
To create what intermediate?
Good.
What kind?
Heteroatom
A
stabilized.
heteroatom stabilized carbocation. So in other words, in acidic medium, the aldol reaction happens by means of that carbon-carbon bond building step, and then we have the positive charge there, and then would you believe that to get rid of that positive charge, all I have to do is lose the proton from the oxygen, my double bond is back, I have C double bond O over here, alpha, beta hydroxy. In other words, beta hydroxy aldehyde or ketone is my product from the acidic attack. The only trouble with that is that it's not as obvious what the final product is going to be. When you start with this, say 2 of that, and acidic medium, I find it difficult to actually see what that final product looks like within a second or two. I take 3 or 4, but it's not as good as carbanion. Carbanions allow you to see the product within a second or two. Okay? So I wanted you to at least see the mechanism in acidic medium. It follows all the things that we've been talking about. But in the future, when you're predicting aldol condensation products, I'd like you to think carbanions formed in basic medium. Okay. So, any questions about the aldol? How are we doing? Everybody's good with this? All right. Here comes the next one. All right. This slide is self-explanatory, so I'll just keep going. Okay. No, it's not self-explanatory by any stretch. Okay. So first of all, it's a claisen. Let's talk about the self-claisen, which hopefully is color-coded with the color you see there. Wonderful. I'm very predictable. All right. So what we have here is the following. This is the only starting material. Notice once again how many alpha hydrogen environments you see in all the reactants. How many? 1. That's because I am going to be generating carbanions at that alpha position. And I want some of the carbanions that I generate to attack some of these molecules that weren't converted to carbanions. So let's take a look and see what that looks like. Here is my unconverted material. Let's make that look like the starting material on the screen. Here we go. Here is OR prime. What kind of a starting material is this? What family of organics does it belong to? Huh? Ester. Okay. So if I come along now with CH minus, here is the baggage hanging off that carbon. Here is more baggage. This is the entire ester group, like that. Okay. This is going to attack that. The first thing that happens is I will generate O minus. In the aldol reaction, when the carbanion attacked the carbonyl of an aldehyde or a ketone, yes, you generated O minus, but that O minus could not regenerate the double bond because of what reason? Why couldn't the O minus from what had been an aldehyde or a ketone just reform that double bond? Because when this double bond reforms, let's show you, here is the carbon, here is CH, with R, here is all that ester baggage. Right? Here is my C double bond O that just reformed. Agreed? What happened to that? You want me to draw it? What's wrong with this picture? Yeah, no one here dare draw anything like that. So, in order to prevent this from happening, what happened to OR prime?
Got kicked out.
I need a 2-word answer, except they're both 4-letter words. What happened to the OR prime? It, I need two, left would be a one forward answer, a two forward answer, meaning the same thing as left. What a
Left.
kid would say.
Left out?
No, not left home.
Out.
No, that's not two four-letter words. Oh, you don't like playing word games, huh? It went away. Yeah, that's what I say. All right, so it went away. So out it goes when this regenerates the double bond. Out goes OR prime minus. And we're not going to leave that in the picture. So here is plus OR prime minus. And let's get this out of the way. And now the question is, how do you describe what kind of a product this is? The aldol condensation product is a beta hydroxy ketone or aldehyde. How would you describe what you see here? I'll give you a hint. Beta. A beta what? No, ain't no anhydride. What family of compound is the major functional group?
Ester.
An ester. So this is a beta something or other ester.
Beta
Not your hand.
keto ester.
A beta keto ester. So that's what Claisen condensations make, at least as the first product. We'll talk about what can happen to this later on. All right? So beta keto ester. And notice what happens when I take an ester that has one alpha hydrogen environment, this one, and let it attack an ester that doesn't have any alpha hydrogen environment. How can this R double prime have no alpha hydrogens? You saw one example already. What kind of alkyl group has no alpha hydrogens? Tert-butyl. So if this was tert-butyl, you can't turn this into a carbanion. What's even simpler than tert-butyl? Think 6 carbons. Benzene, not phenol, phenyl. Yeah. All right? So if that were a monosubstituted benzene or a tert-butyl, that's it. Hell, if this were H, there would be no alpha hydrogens because the H has to be on a carbon next to that, and with just H there, there's no alpha carbon. So that means that only this can form the carbanion, only that carbonyl carbon gets attacked, only that gets kicked out, and the way we're managing the fact that only this forms the carbanion and this gets attacked by the carbanion is because which of those two reactants is where in the logistics of this reaction? Which one is mixed with the base? The one without, right? Well, notice what the base happens to be. Happens to be OR prime. The very thing that you're kicking out. So what would happen if instead of using OR prime, I used what you would normally think of first when you thought base, like OH minus? What would OH minus, when you're heating this thing, do to that carbonyl? OH minus. I need an A word that means fight. That's right, attack what? OH minus.
Oh, it would attack the carbon.
This carbon.
Which is electron. Yeah.
Yes, that carbon. As well as that carbon. Right? Yeah. And temporarily turn these double bond O's into,
Oh my.
and the O minuses would then ask themselves, what?
What is this?
Can I I would have said regenerate, but okay, yeah. Regenerate the double bond by kicking something out. If the OH minus attacking these carbonyls was successful in kicking out the OR prime, what kind of a family of compound would you now turn this into? And how likely would it be in the presence of an OH that's acidic, would you be in creating a carbanion at the alpha position? And the answer, none. No chance whatsoever. Which is why the base you use has to be identical to the alcohol group you're kicking out. Because this is going to be constantly attacking those carbonyls. It will be kicking this out, but because it's OR that's doing the attacking, guess what? Has anything changed? No. Okay, so you can get away with it. So here, because there's no alpha set of hydrogens at this site, this attacks that, this goes away, and that's reflected in your product. Notice there's a byproduct, alcohol, eventually when this is worked up. All right? That's the self versus cross Claisen condensation. Are you good with this? These two are the mainstay of this topic. Aldol, Claisen. Now here, take a look at this. Here we have a diester, except the two ester groups are in the same molecule. Notice that I have 4 CH2s between the two carbonyls. How many alpha hydrogen environments do I have in this reactant? How many unique alpha hydrogen environments do I have? One. There you go. Whether it's this, whether it's that, there is only one CH2 adjacent to the carbonyl. And it doesn't matter which one of those two CH2s I turn into the carbanion, because wherever that carbanion is, let's say I make it on the left, where is that carbanion going to attack? Answer, dog biting tail. It's going to attack there. If the CH2 carbanion carbon was on this side, then this would be the carbanion. It would then attack that. Either way, I am in the business of making 6 and 5-membered ring systems. What kind of a compound is the cyclic system? Answer, a beta keto. This is beta, alpha. Here's your ester group. This is a beta keto ester product. That's exactly what Claisen condensations make. Okay, so let's put that in there. So if you were to see something like this, the question is, would you be able to dissect this mentally and say to yourself, maybe I can see what it looked like by cutting the bond right between the alpha and beta carbons? Because the carbon over here is certainly alpha to both of these, but here is the ester, this being a Claisen. You know that the ester has to be the starting material, so that what we can say is that this was the carbanion, this came along for the ride, and this used to be an ester, but it was attacked by that carbanion internally. This will take some getting used to. You need to make yourself the time to get acquainted. Are you okay with this? And of course, the person who developed the cyclic Claisen is being given credit for that particular permutation, and his name was Diekman. I suspect he was probably Dutch, and it's named after him, and you need to know that name and associate it with what happens. Question. Easy for you to say, cyclization? No, It's an internal condensation leading to cyclic product. No, it's called the Dickman condensation. Yeah. It's just a variety of Claisen. If you can remember it that way, hopefully it will be retained. It's a variety of Claisen. How are we doing? Are you good? Yeah, please. Okay, so let me draw this out so you can see how it actually happened. Which one would you like, making the 6 or the 5? She wants 5, she's got the floor. Okay, so you ready? Here is my ester, C5, and that's attached to CH2, 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 how many CH2? 4? Okay, here's 4. And here is that other ester. Okay, too lazy to draw carbon. So, I'm arbitrarily going to use OR prime negative to rip off one of those 2 hydrogens. You drawing that for yourself? Okay, what's the result? The result is I've now created a byproduct alcohol, R prime OA. Don't care about that. More important is that I've created a carbanion alpha for one of the carbonyl. And because nature loves 5 and 6 membered rings, and this molecule is moving around at any temperature above 0 degrees, sooner or later, let's just do it like this. Here's my carbonyl, here is my OR prime. This is going to find that. Okay with that? This is temporarily going to be displaced onto oxygen. It's going to be replaced to regenerate the double bond, and in so doing, out goes that. Okay? And as soon as that goes out, what am I left with? I'm left with a bond right here. This is the bond that was made by the condensation. If you wish, the Diekmann condensation. And what size ring did I create? 1, 2, 3, 4, 5. That's it. Are we good? All right. Let's try one more that has some relationship to the first 2. This is the Refermatsky. If you look in the index of your textbook, I don't know whether you will still be able to find Refermatsky in the textbook. They might have it as an aside, as some homework problem maybe, but I don't have much faith that you'll find it. So here is the Refermatsky. Okay? So, how does this have any relationship to the previous 2 condensations? In the aldol, we were making beta hydroxyaldehydes of ketone. In the Claisen, we're making beta keto esters. What's this making? Yeah. Can you see how it's sort of half and half? We've got the beta hydroxy part from the aldol, and we've got the ester part from the Claisen. This is literally a hybrid reaction. I don't know that Refermatsky would have thought so. He thought he invented it, but I couldn't even tell you the timeline when this was invented relative to the previous 2. But how does it happen, you might ask? All right. First of all, we're again starting with what looks like an ester. What position is this in the ester?
Open.
Alpha. And notice what's attached to the alpha carbon.
Halogen.
A halogen. So, that halogen attached to the alpha carbon of the ester is going to be reacting with metallic zinc in some suitable solvent. This slide goes back a long time when benzene was routinely used as a solvent. No one in their right mind uses benzene any longer. It's too toxic, it's bad for the liver, causes cancer, it's just bad. So some other solvent, maybe something like toluene that's less toxic. But the point is, what does this remind you of, hopefully? I'm using a metal, and I'm using a halogen on a carbon. Yeah, this is the zinc analog of a Grignard. In other words, the active ingredient that you're making, and I don't know who's going to get credit for, I guess Refermatsky could take credit for it. It would just be Br with zinc in between. It behaves exactly the way a Grignard does. In other words, that this is going to think it's electron rich because this is electron deprived. But there is one significant difference between the zinc analog of a Grignard and a real Grignard. Because if this were a Grignard, look at the rest of your starting material. What kind of a compound is the rest of your starting material? And do you know any reactions between Grignards and esters? The answer is yes, you do, and you have to remember it right this second. Yeah? What does a Grignard do to an ester? That's right. How many Grignard molecules attack an ester carbonyl? Two. Exactly. So in other words, if this were magnesium, the whole reaction would die right then and there. But because this is a less reactive version of an organometallic, we can get away with having an ester group around so that this carbon can attack that ester group. So where is that other ester group? Actually, it's not an other ester group. It's going to be an aldehyde or a ketone. And if we choose this generic aldehyde, then what's going to happen is this is going to attack there. This is going to pick up the zinc and the Br. So what you're going to have is all this baggage untouched, CH2, C double bond to O, OR prime. And what's attached to that carbon now that you've made the new link? Answer is the carbonyl carbon of the old aldehyde or ketone, which became OZNBr with an R group here, H over here, let's say. And as soon as I carefully acidify, off comes the ZNBr, and in its place, you end up generating, just as you would with alcohol formation, an alcohol. And where is this alcohol? This is at the beta carbon relative to the ester carbon. And this is what the Refermatsky reaction does. How are you doing? All this evening is really meant to do is just to give you an introduction to this, to give you a basis for it. How long it takes you to assimilate all this is an individual dilemma, but I'm going to let you deal with that. We have time, I think, for the Davidic. Let's show you what this is about. This is not going to resemble the first three sets of condensation. Nevertheless, it has a common theme that I'm going to try and convince you of. All right? So, what is this slide trying to show you? First of all, the answer is too much. So, what I'll have to do is explain. And it's more or less color-coded. First step is we are going to make a phosphonium salt. What's a phosphonium salt? Well, phosphorus is in the same family as what more familiar element? Nitrogen. And if you put 4 bonds around nitrogen, what have you created?
Ammonia.
And what's the name of that salt? No. It's not an amine. No. No. It's an ammonium salt. Ammonium. Well, this is the phosphorus analog of ammonium. It's called phosphonium. What is phosphonium? It's a quaternary phosphorus atom that is now positively charged, just as nitrogen would be, because it no longer has lone pair electrons. And how did you make it? You took this tri-substituted phosphorus, and the most convenient one, readily available commercially, is one that looks like this. This is called triphenylphosphine, and when you come along and you have, let's say, RCH2X, most notably this is a primary alkyl halide. What's special about primary alkyl halide? The carbon bearing the leaving group is what?
Electron deprived.
I'll give you a hint. What New York City isn't.
Oh, Syracuse.
Uncrowded. There you go. So, what kind of reaction are we running? Most notably, SN2, which requires that carbon be uncrowded. If you attempt this on anything other than a primary carbon or methyl, it's wrong. Not going to happen. Okay? So now I have this. I have my phosphonium salt here. I have CH2R. Right? Well, if you recall, in all the previous examples that we've discussed this evening, we had alpha hydrogens. Alpha to what? In other words, I put down CH, I call this alpha. Alpha to what? To a carbonyl. Ready? What's true about this carbon in the carbonyl? What's true about that carbon in the carbonyl? Electron deprived. Okay. So, here I have hydrogens on a carbon attached directly to a positive atom. What do you think is true about those hydrogens? The fact that they're in proximity to this positive center allows them to be pulled away by what kind of a species?
An electron deprived species?
Ooh.
No.
An anion. Okay, so you ready? Watch this. What do you see in this next step? You see sodium hydride. What's sodium hydride? Sodium hydride is just H minus. Sodium is just there for the formula. What is H minus going to do to one of these two hydrogens? It's going to rip it off. It's going to form H2 gas. Goes away. Hopefully it doesn't explode in the process. And most importantly, what did we just generate? We just generated a carbanion right next to an electron-deprived atom. Isn't that what happens in the alpha carbonyl systems that we talked about all through? So you might be asking the next logical question then. But when we created the alpha carbanion, when we had a carbonyl group, what could be said about that negative charge? Did it reside entirely on that alpha carbon atom? Or was there any possibility of delocalization? What do you say? Is the carbonyl group right next to a C minus? Is there or isn't there delocalization of that negative charge?
Yeah.
Yes?
Yeah.
Guess what? There's the same delocalization here. But you're probably saying to yourself, I don't see any carbonyl next door here. How can there be any delocalization, right? You ready for this? This pair of electrons on carbon sits in what kind of an orbital on carbon? P orbital. What's a p orbital look like? Big dumbbell. There's your electron pair making this carbon negatively charged. Next door is an element from what period of the periodic table? What? The third. What kind of atomic orbital exists for the first time in the third energy level? What shape are d orbitals? Four-leaf clovers. You ready? One of those four-leaf clovers is empty. Guess where that pair of electrons can be delocalized into? The empty four-leaf clover. So for the same reason that you can form alpha carbanions adjacent to carbonyl groups, you can form alpha carbanions adjacent to P+. Because the electron pair can be delocalized into that d orbital. This, for what it's worth, is called dp pi bonding. And as much as it pains me to have to tell you this, there are many textbooks and many instructors that just love to draw this species, not the way I've shown you as a carbanion, but as the following. That. I mean, if you believe in this phenomenon, then you're not going to be averse to drawing that. Because I don't believe in that phenomenon, I particularly don't want to express it that way. I want you to think of it as a carbanion. Okay? So now what? Well, if you come along now with C double bond O, and this is from an aldehyde or a ketone, can you see a reason for this? Which, by the way, when you have a negative charge next to a positive charge, this is called this. Anybody want to pronounce that? I'll give you a hint. Homer.
You?
Will. That was so important. That concept was too weighty for me to hold in one hand. All right. Yeah. So this is called an illid. Sometimes you'll see it spelled with an E. I don't know what your author prefers. Either way is okay by me. It's an illid. But when you come right down to it, it's an alpha carbanion. Same as in the previous three reaction types. And what's the whole point of this? The whole point of this is that you can, once you've made this, you've done what you needed to, watch this. We are going to end up making triphenylphosphine oxide That's the byproduct. I don't really care about that. But the more important product is going to be, here is, instead of C double bond O, C double bond CHR. That. Okay? So you're saying all of that just to make an alkene? Not only that, but this won Wittig the Nobel Prize, no less. So let me show you an example. Right?
What about it won the Nobel Prize? Discovering that this happened or documenting the mechanism?
Showing
it
the
took all of it.
utility of this and possibly elaborating the mechanism. Right? So let's show you. Let's say I want you to make, let's say, that. No, I don't. Yeah. Okay? Let's say I want you to make that. Right? Based on your present knowledge, barring the video, you have just time left to talk about it. How would you make this alkene? The most familiar alkene generating reaction you know involves dehydration of alcohol. Okay, so you ready? What alcohol would you have used in a prior life to generate this? Where was your OH? I'll give you a hint.
2.
It could either be here or it could be here, right? Okay, so you ready? Let's say I put 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Let's say I put it here. I dehydrate. Do I get only that alkene? What's the problem?
You get some of the
I will get some of the minor product. Bad news, you put it in the wrong place, okay? So now I put it over here. Yeah?
Even more.
It'll go there, but it will also go there. In other words, the old-fashioned way always gave mixtures of alkene products. And anybody who's ever taken Organic 1 lab with us knows that alkene products stink. No one wants to be distilling mixtures of alkene. That is really stinky. So, you ready? Along comes Wittig, and he says, you want to make that? No problem. Mentally dissect this. Which one of these pieces would you like to be the carbonyl? You pick. Doesn't matter to Wittig. He's dead. What? The 2 carbon. You want that to be the carbonyl. Okay? So what does Wittig do? He generates a 1, 2, 3, 4. 1, 2, 3, 4. This carbon will have negative charge. This carbon will be attached to a phosphorus with 3 benzenes. And you combine these two, and guess what your only alkene product is going to be? That one. Not only that, but you could have made this carbon the carbonyl, and made that one the ylid carbon, and you'd still get only that. That's worth a Nobel Prize. So on that note, I'm going to have to let you go. Does anybody have any questions? Amanda, do you have any questions? No. Okay. So with no questions. All right. So we'll take ylid formation followed by attack. And
I have a question.
yes.
When we talked about, we were talking about aldol condensation, the cross method
Right.
in acidic conditions.
Yes.
I could not picture the product of what you had drawn. Would you mind redrawing it since we have
Okay.
5 minutes?
Yeah.
charge.
There it is. You had CH3, C, and then a carbon.
So, well, the thing is that it's easier to picture the self aldol
Right.
under acidic conditions.
Yes.
But if you go the cross,
Okay.
well, let's see. Let's take something like this.
It might not have been the cross method. I just had
Wait,
acidic
wait.
conditions.
Let's
Okay.
say, no, this thing, let's do like this. We can still get away with it if we have something like this. Okay, here are two aldehydes. Which one of these is the one that's going to be capable of forming carbanion?
The bottom one.
Actually, not carbanion, but it's the bottom one, right? So here's the thing. In acidic medium where there are no carbanions, both of these carbonyl groups can be protonated. Agreed? So let's do that. We're protonating both of them. This forms heteroatom stabilized carbocation, so does this. But in the acid catalyzed version of the aldol, what does the heteroatom stabilized carbocation have to attack? And the answer is the enol version. Can there be an enol version for this? Nope. So that's how it works. In other words, not all of this is going to be in the form of the carbocation. Some of it will end up turning into this double bond COH, and now I think you can see that this version of that will attack here, and that will give you your condensation. The only trouble is,
So where does the double bond for the O regenerate at? That's
so
what I'm
here's
mostly
the-
confused
So here's the
about.
problem. Instead of having this attacking a version of itself, you needed to attack this. This is the other species present.
Right.
So if I have this attacking that, I can do this under acidic medium. The only trouble is I can't explain away that I won't get a mixture.
Okay.
That's the hard part with acid catalyst. I can't just,
Gotcha. That makes sense.
although, I don't know, you can still make a case that says, let's have the formaldehyde in with the acid. So what? If the carbonyl oxygen is protonated, it'll come on and off. And then I'll drip in the one with the alpha hydrogens. It's the one capable of forming enol. All right? The only trouble is the enol is not what I want. I want that.
Yeah.
So you'll have to make a case that before this protonated version of the one with the alpha hydrogens enolizes, it'll attack that first. And that's a tough case to make. I don't want to make that case.
This is specifically crossed, you said?
Yeah, I would
Okay.
say that the crossed aldol doesn't lend itself very well to acidic conditions because it makes mixtures. Whereas you can control the carbanion approach. Yeah. So, what are you going to do?
Feel better, man. We'll catch you
Yeah,
later.
that's where they would have put it. Yeah, what's the requirement? Say never.
Yeah.
Oh. No, put it on an hour.
He said boil, so I don't know.
Well, as long as, the time it takes me to walk from the office to the classroom here, it doesn't have to be the sign in.